So far we have learned how to estimate detection probabilities. We'll now talk about how we can use these to estimate abundance or density. In this lecture, our objective is to estimate abundance of animals. In order to do this, we will speak about detection probabilities around the detectors. We'll learn about how the average detection probability in the study area or in smaller regions of the study area, what it looks like. Lastly, we'll have a look at some sample model output from the ASCR package. So up to this point, we've looked at detection probability around the animals. What is the probability of an animal to be heard at a given distance from it, to be detected? We'll now look at the same problem from the perspective of the detectors. What is the detection probability within the same concentric distance rings around the detectors? As the detection function depends on distance, and it does not matter which way you measure distance, this is the same as before. In other words, the probability of an animal to be detected is the same as the probability of the detector to detect an animal. So we've just seen that we can plot the detection probability around a detector instead of around the animals. So we can do this. So we can do this for each of the 16 detectors here. So how does this work then when we don't just use a single detector, but multiple detectors or an array of detectors like in our example? Turns out when we have multiple detectors, we can combine the probabilities of all detectors into a map of detection probabilities. In this case, where all detectors operated equivalently, this is an easy exercise. So you can see that they are still the highest, the detection probabilities are still the highest near the detectors, but don't really drop that much until you get to the outer edges of the study area where we see the lighter shades of orange and yellow. So if any animals were within the darker regions, we would have a very good chance of detecting it. We're going to put some animals into our study area now. Each blue point is an animal. There are 100 blue points, and these represent the whole population in our study area. So capital N is 100. Some of these animals are detected, which we turn green now. These are 71 out of the 100. So little n is 71. These are the only ones we observe. We don't actually know anything about the blue ones. So let's just focus on the green ones for a moment. This is all we observe, and somehow we need to estimate how many we missed. So how many blue ones were there in addition to the green ones? Both of them together give us the total population, the quantity we're interested in. Therefore, we need to estimate the detection probability in the study area so that we can determine what proportion of n we observed, or in other words, how many we missed. So what we'll do now is add the detection probabilities for all detectors combined to the image, and we'll go through the process of how we use these to estimate abundance and density using a simplified example. In the first step, we'll divide the study area into small regions as indicated by the black lines. I used a relatively coarse resolution here to show you a simple example of where the estimates come from. In reality, this is done on a much finer scale. We'll then go ahead and look at how many animals were we detected in each region, which we'll call little ni, where the little I denotes the individual regions. Note that I didn't put the subscript I onto the plot on the left. But for example, in this little square, this is the first square, so for this square, little I would be 1, and therefore little n should actually be little n1. So we also need the average probability of detection in that region, which we add now, which is just an average of all the pixels we see in the region, and we'll call this little pi. So we have a little pi here, and the hat indicates that this is an estimate. This is something we need to estimate. And so p equals 0.4 here in the top left square. This should actually be little p1. So we can use these to calculate what the abundance was in the region, which we'll call capital Ni, which we see here. This also has a hat on because it's an estimate. So let's have a look at the individual regions. We know little n for each region. And we know the average detection probability in each region. And from that, we can calculate what the capital N I's are in the individual regions. So this for each region is given in the bottom row for each of the little squares here. So in the first one, for example, the little n1 was equal to 2 and p1 was 0.4. So the estimate of n1, capital N1 in that square was 5.5, and so on. So we can then use these to obtain an estimate of abundance of capital N by summing up of all the Ni's. In this case, this equals to 110.5. Next, we're going to estimate density for each region, which is the number of animals per unit area. For this, we also need to know the size of the region, which we'll call AI. So little AI is the size of the region of each one of those little squares. And density in each region is the number of observed animals in the region, little ni, divided by the probability of detection, pi, divided by the size of the region, ai, which is 500 meters by 500 meters. So lastly, we can also get an estimate of the average density in the whole study area, which is simply the total abundance estimate divided by the total area in the study area. Notice that I changed the units to hectare in this last step, which is what is generally done using the R package ASCR. Otherwise, the density estimate would be very, very small if you left the units as meters. Let's talk about now about the SCR model. What kind of parameters do we have in an SCR model? Let's look at the simplest scenario first. We always have two models in an SCR model. One is the density model, which we just talked about, and one is the detection model, which we spoke about in the previous lecture. The density model models how many animals we have in our study area per unit area. In the example we have seen in the previous lectures, this was even across the study area. In this case, the density model is very simple and just consists of a single value. So the simplest density model has one parameter, which we call beta 0. Now to the detection model. Here we model the probability of detecting animals at a detector given their distance to the animal. We have already learned that the simplest detection model has two parameters, which are sigma and G0. G0 can roughly be described as what is the probability of detecting the animal if it is at the location of the detector or right next to it, and sigma, the parameter defining how quickly the detection probabilities drop off with increasing distance from the detector. So at minimum, there are three parameters to estimate for the SCR model: beta, G0, and sigma. Back to the density model now. We could easily imagine a different scenario in which animals are not uniformly distributed, like in this example now. So here we have a density gradient from north to south, as shown on the plot with the green dots. And this can be accommodated by fitting an extra parameter in the density model, which is beta 1. This is the coefficient associated with the y-coordinate. Note that the formula for density looks a bit more complicated now, especially with the exponent. This is something we don't really need to worry about at this point. It is simply a link function that prevents us from accidentally obtaining negative density values. So this constrains density values never to go below 0. You can also see in the plot how the line now flattens off towards y equals 0. Sorry. We'll now have a look at how we can fit a spatial capture-recapture model with functions from the ASCR package in R. We use the function fit.ascr to fit the model. This function requires various objects as input, which we'll talk about in the next lecture in detail. For now, we just fit the model and see what the model output is. So in order to fit the model, we use the following code. We give the model a name, mod1. Fit.ascr is the model fitting function. And these are the three objects that fit.ascr requires as input. We can have a look at a summary of the model using the summary function. And this points out the estimates of the model parameters, which should be, this prints out the estimates of the model parameters, which would be familiar to you at this point. Here we have the estimate of density in the study area with the standard error. This is always given in the number of animals per hectare. Some units are hard-coded into the functions, and one of these units is hectares for density estimates. We'll talk more about this in the following lecture. Here's the estimate of G0 with its standard error. And this is the estimate of sigma. There are other functions you could use to extract the coefficients or standard errors from the model. For example, you can use the function coef to get the coefficients. You can use this function to get the standard error. And this function to get the 95% confidence interval of all three parameters. In your papers or reports, you will likely have to present an estimate of variance along with your estimates of the coefficients. So these functions come in really handy to get these. And then it is generally up to you in which way you present your estimate of variance, whether you present standard errors or 95% confidence interval. You can also have a look at the detection model using this function. This will show you a plot which shows how your detection probabilities decrease with increasing distance from the detector. This might seem a bit abstract, but it's actually a good exercise to do this as a biologist, because with the knowledge you have being a biologist and what you know about your species, you can check whether the model actually makes sense biologically. So let's have a look at what the plot tells me. For example, at 0 distance, the line is at 1, which tells me that the model estimated that I had perfect detection at 0 distance. This means if an animal was right next to the detector, there's no way the detector would have missed it. I can also read off the value for 200 meters. Here was at about 0.7, which means at 200 meters my probability of detecting an animal was about 70, and I would have missed 30% of all the animals at 200 meters. I can do the same for 500 meters and see what my model estimated at that distance, and here was about 12%. And at 800 meters, I already did not detect any animals at all anymore. So you can use this to check if the estimates make sense biologically. Does it sound about right that I have no chance of detecting an animal or any animal at 800 meters like my model says? You can ask yourself questions like these. Lastly, we'll convert the density estimate and its CI into abundance estimates. Remember, we fitted the simplest model and assumed constant density around the study area. Our density estimate was 0.169 animals per hectare. 1 hectare is 0.01 square kilometers. The study area was 2,500 meters squared, so 6.25 square kilometers, which equals 625 hectares. And we learned how abundance and density relate to each other in the previous slide. Abundance N is density times the area, so 0.169 animals per hectare times 625 hectares equals 106 animals. We do the same thing with a 95% confidence interval. Just multiply them with the area in hectares, which gives us 78 and 133. So then our abundance estimate comes to 106 animals and this confidence interval of 78 and 133. How did we do? You might remember that the total number of animals was 100. So our estimate of 106 is pretty close, and our confidence intervals overlapped 100, which is important. So the true value of abundance was within the confidence interval. That's the part to look out for here. Of course, in reality, you don't know what the true number is, but in this case, we can check it and see if there's any potential issues here with this analysis. Here are some of the key points to remember from this lecture. We can estimate the expected detection probability in the study area using the detection probabilities around the individual detectors. We can use the expected detection probability to adjust the observed number of animals for those we missed. The SCR model always consists of a density model and a detection model, and the function fit.ASCR estimates the parameters of the SCR model fitted to the data.